Good morning, everyone. Welcome to the security seminar here at the Purdue University. It's my pleasure to introduce today's speaker. Vitaly Shmetkov is an assistant professor in the Department of Computer Science at the University of Texas at Austin. Before joining UT, he worked as a computer scientist at SRI International. Vitaly's research focuses on tools and formal methods for automated analysis and verification of secure systems, as well as various aspects of anonymity and privacy. Vitaly received his PhD in 2000 from Stanford University with thesis on finite state analysis of security protocols. Here's Vitaly.
Hi. So, first of all, thanks for inviting me here. And the work I'm going to be talking about today is joined with Arvind Narayanan. This is, I've never talked about this before. This is actually the first time I'm talking about this subject. As a matter of fact, the work on which it's based has not been published yet. So we're still figuring out how to do some of the proofs. So this is, in some sense, this is work in progress. I'm pretty sure everything I'm telling you today is correct, but I hope you understand that you're first people in the world to see this. I've never talked about this before, so I decided I'll try it out on you. And the topic I'm going to be talking about is obfuscated databases. And here is, let me try to give you a motivation for what I want to do. So suppose you have a phone book or an email directory which contains some sensitive information. And you want to control how people access this phone book. So here we have a list of names, a list of phone numbers, a list of emails. And what you want is to give this phone book to people in such a way that it's easy to look up the number if you know the name. But if you don't know the name, the phone book does not reveal anything. Okay? So you can think of them. Okay, so one way to think about it, you can think of some sort of spam protection, anti-spam in online directories. You want to publish an email directory, so if you know the name of the person, it's very easy to look up the email. But if you just want to go and harvest the entire list of emails, there is no way of doing this. Okay? So this is a little bit of a weird notion, so I invite you to think a little bit just on this simple example. They'll get a little bit more complicated later on. What it means. I'm saying that some forms of access should be easy and some should be hard. Okay? So easy to look up the number if you know the name, but if you don't know the name, it does not reveal anything. Like you cannot go to this and get a list of names out of it. And you cannot get a list of emails. The only thing you can do, you can supply a name and get out the corresponding phone and email. So let me try to make what I just said a little bit more precise mathematically. And I'll do this on the next slide, but here it's a little bit more rigorous. That is, somehow I want to mutate the database so that it starts looking like a lookup oracle. That is, the database is like a function from names to phones. And what does it mean that it's like a function? I'll give a mathematical definition in a moment. But to be like a function, this means that the only query that is easy to compute on the transformed database or obfuscated database is something like this. So give me the phone where name is some name supplied by you. Because this, asking this question, this corresponds to evaluating this function. But nothing else is feasible. So if you don't know the name, you can't look up the phone. You cannot extract the list of phones. You cannot learn any names you don't already know. So, and this is interesting because now I'm saying I'm taking a database, and the database is just a table with information for the purposes of this talk. And you know, if you have a table, you can look at this column, or you could ask all sorts of complicated questions and access it in unlimited ways. And now I want to transform it, obfuscate it in a way that it becomes indistinguishable from a function, from names to phones. So this is like a fairly non-trivial task in general. So why do I want to do that? Well, the usual notion of privacy, and a very useful notion of privacy actually, and a lot of research has been done on this, is that I don't want you to have any access to my data. Maybe you can have some access to joint statistics, maybe you know some global parameters, but as far as my individual records are concerned, there shouldn't be any way for you to access them. And part of it is because if you get my individual record, I cannot really control how this data will be used once it's released. And this is a very good notion of privacy and a very useful one. Now, the notion I'm talking about is slightly different, and I'll give you some applications for which it's useful. And my notion of privacy here is that I'll actually give you the data, but I'll control how you can use the data I've given you. So this is a way of trying to retain control over the data after it has been released. And as you can see, it's a much more difficult problem. So it's very likely that a lot of things that you want to do, you just cannot do in this way. So somehow I want to scramble or obfuscate the data in the database so that when I give the database to you, I know exactly the ways in which you can access it and the ways in which you cannot access it. And applications of this are sharing data with untrusted parties. That's sort of common. Publish a database online, for example, or distribute it to other people, but prevent people from harvesting information indiscriminately. So my email directory example. You give an email directory to someone, and you want them to be able to look up the phone if they look up the email if they know the name, but they cannot abuse it by extracting the list of emails and send spam to everybody. Okay, so I hope you see the difference between this notion of privacy and what you might be used to as the notion of privacy. So here my goal is to mutate the database in such a way that when I give it to you, I control how you can access it. Okay? So here is sort of the big picture. So what do I mean that I control how you access it? Is that I want to say that certain questions, certain queries on this database are easy, and everything else is hard. Okay? Hard as in computationally infeasible. Now, this is a very strong requirement. Now, I am not saying that there's going to be a trusted third party that controls how you use the database I give you. I don't rely on any access control software. I don't rely on any ad hoc schemes for scrambling the data. I actually want a proof, a mathematical proof, that there is nothing you can do with the data I give you beyond what's allowed. Okay? And again, this is a strong requirement because having provable security is a much taller order, if you will, than having just security in some abstract sense, because I want to have a mathematical constructions based that has this property, that some questions you can ask, some questions you cannot ask. Okay, and of course we'll have to use cryptography to do that in some fashion. But I hope that you understand that I'm after something fairly ambitious here. That is, you know, I'm not going to rely on any sort of trusted intermediary. I'll just assume that the data I give you is being evaluated or analyzed on a completely untrusted platform. Basically, the adversary can do whatever he wants. And then I want to make things that I don't want him to do. I want to make them, well, I cannot make them impossible. At least I don't know how. But I'm just going to make them very, very hard. I'm going to make them infeasible. Yes?
So just to be clear, a query will either be answered easily or it's unanswerable. There is no issue of partially answering a query. Right?
I'll get to that in a moment. As a matter of fact, it's an excellent question, and I'll get to it in a bit. So hold that thought. It's a good thought. Okay, so what do we know about obfuscation in general? So what is the state of the art on this problem? So first of all, there are a lot of ad hoc obfuscation schemes out there. Most of them, actually all of them as far as I know, come without proofs of security, and many are broken. Like one of the more famous examples, there was a company that was publishing obfuscated deaths. So this was they give you a software for computing deaths with a key that's somehow hidden inside the program. So you cannot extract the key. So this is sort of a way of converting symmetric cryptography into asymmetric cryptography, like secret key into public key. And it turns out there was a famous attack by Banet, Jacob, and Felton on that you can extract information from it. So ad hoc obfuscation, so people propose things usually, as soon as someone looks at it carefully, it turns out not to work as expected. A few years ago, there was a very famous paper by Barak and many other co-authors in crypto on impossibility of general purpose obfuscation. And this is a very strong paper, and it's strong in one sense and weak in another. So it's, as always, it's all in the order of quantifiers. They say that there is no obfuscator that works on all functions by showing that there is a class of functions which cannot be obfuscated. Like, for example, encryption as an example of a function that doesn't seem to be obfuscatable. But this is impossibility of general purpose obfuscation. I'm not after general purpose obfuscation here. You know, when I say that I want a database to look like a lookup oracle, you know, I want to obfuscate lookup of data, okay? I don't want to obfuscate any polynomial time computation. So in that sense, the fact that general purpose obfuscation is impossible doesn't really tell me anything for the purposes of practical obfuscation, because who knows, maybe the thing that I want to obfuscate is actually efficiently obfuscatable. So in some sense, this impossibility result doesn't really affect anything I'm going to be talking about. It doesn't say that what I'm planning to do is impossible, so, or even that this class of problems is, the class of problems that are associated with obfuscated databases is impossible. So it's good to know that it exists. Now, for a very limited class of functions, which I'm hoping to extend in this talk and in this work, we know that they're obfuscatable. There was a paper in Eurocrypt just last year by Ben Lin, Prabhakaran, and Amit Sahai, showing that point functions are obfuscatable. And point functions, think of hashing. Think of Unix password hashes. So that's an example of obfuscating equality. So somehow you want, like when you give someone a hash of a password, there is no way, you hope that if the hash function is good, there is no way to extract the password from it. And yet, so think of it as a function that evaluates to 1 on only one point where the password is correct, and on every other password it gives 0, okay? So it seems like hashing provides a good obfuscation of this point function, and in fact it's provable in the random oracle model, or you can prove it, if you don't like the random oracle model, you can prove it if you just have a good hash function. But point functions are obfuscatable, and we use it every day when we type in our passwords. And that's, as far as I know, that's all that's known about provable obfuscation. That's general purpose obfuscation is impossible, point functions are obfuscatable. And databases are somewhere in the middle. So, well, let's see what we can do. So, okay. So the basic approach that I'm going to use in presenting this and defining correctness is based on simulatability and the ideal functionality. And if you are familiar with cryptography, with modern theoretical cryptography, this will be very, very recognizable. And if you haven't had that experience, then maybe it's a little bit obscure. So I'll spend some time trying to give you an intuition for why the definitions look like what they look like. So, but I have to apologize if you're familiar with work on secure multi-party computation, these definitions are going to look completely standard to you, so there will be no surprises here. So it starts by defining what's called ideal functionality for obfuscated database. This is what we want our database to look like. So I said we want our database to behave like a lookup function. So this means that the ideal functionality is the lookup function. And the ideal functionality, it's secure by definition, okay? Because it describes only legitimate queries and or access patterns. Like if I say it's a lookup function, that's immediately clear. Like if the only thing you have is a lookup function from names to phones, then there is no way to evaluate this lookup function so that it gives you a name in response to a phone. Its argument is a name, and it returns a phone, okay? So this is the ideal functionality. That's what I want my thing to look like. And now I'm saying that obfuscation is good, or it's a real obfuscation, once I define the obfuscation algorithm, is if there is no efficient algorithm, that is, no efficient adversary, can tell the difference between the obfuscated database and something that's simulated in the ideal functionality. So what I'm after, I want to argue that my obfuscation algorithm is good if the result of this algorithm does not leak any information beyond what's given by the ideal functionality. So it's kind of like a two-step reasoning. The ideal functionality I define is secure by design, okay? So, and if the real obfuscation does not leak any more information than the ideal functionality, this means that the obfuscation is good, that no more information can be extracted from it than permitted by ideal functionality. And as I mentioned, this is a standard notion in secure multi-party computation. Of course, here there is no multi-party computation. I'm just giving you the data. But the definitions are exactly the same in some sense. Okay, so any questions about this? So this kind of really high-level idea of defining what you want your thing to look like, and then arguing that it leaks no more information. I think I have a picture even here, like trying to explain this intuition. So on the left here, blue, we have the original database, which is obfuscated. And on the right, we have ideal functionality, which is secure by definition. And the claim is that if there is a simulator, if there is an efficient algorithm that produces a fake obfuscated database, so this fake obfuscated database is secure by definition. And the reason it's secure by definition is because it is created without access to the original database. It's only created with access to the ideal functionality. So the simulator who creates it does not know what is in the original database. All the simulator knows is what's permitted by the ideal functionality. So that's secure by definition. That cannot leak any information because it's not even based on the real database. Okay? And now the claim is that if no efficient, that is no probabilistic polynomial time adversary, can tell the difference between a fake obfuscation, which doesn't leak anything by definition, and the real obfuscation. This means that the real obfuscation based on the real database does not contain any more information than the ideal functionality. And so for the first example, I'm just going to use it to show, just for a simple lookup function, how this can be done, how you can scramble the database so that it's not all that different from a lookup function. Okay, and as always, it has to be, they can tell the difference with more than negligible probability. So this is computational security, not information theoretic security. We're just saying that it's computationally infeasible to tell the difference. Okay, so now going from this, so this is the formal definition, and I'm giving it for a lookup function. So let me try to go through it so that it doesn't look so scary. So we have a database, and let's just for the purposes of this talk, I can do it in a more general setting, but for the purposes of this talk, the database is a list of pairs x and y. Okay? But the ideal functionality is a function which, given x, returns the list of all y's such that there is a row in the database where this y appears next to x. Okay? I hope you see the difference. Like if I have just a list of x and y's, I can just look at y's without supplying any x. But the only way to extract y from ideal functionality is to supply x. And if I don't know x, then there is no way for me to extract any y's from the ideal functionality. So it's clear that ideal functionality, the lookup function in this case, leaks much less information than the original database. And in particular, it determines how you can access it. That is the only way to get y's, to supply the corresponding x. And then I say that an obfuscation, that something is an obfuscation of the database if it satisfies three properties. Okay, there are only two on this slide. I'll tell you the third a little bit later. So the first one is probably correct retrieval. That is, with overwhelming probability, if you give it x, what it returns is exactly the same as a lookup function would return. So this is just sort of obvious thing that, this is just saying that the obfuscation has to be useful, that it has to preserve with overwhelming probability. It has to preserve the functionality of the lookup function. So this has nothing to do with security. This has to do with correctness. But security comes from this thing which is called the virtual black box property. And that's the name that was used by Barak and company in the original paper on the impossibility of obfuscation. And this says that for any polynomial time, probabilistic polytime adversary, there is a simulator which produces the same output. That is, here the adversary is working on the real database. But here, the simulator is working just on the ideal functionality. It actually gets a bunch of ones. It doesn't get access to the real database. And if anything that the real world adversary can learn from the real database, the simulator can learn by accessing just the ideal functionality, I mean, from the real obfuscated database, this is just saying that with overwhelming probability, there is no more information contained in the obfuscated database than in the ideal functionality. And the third, and again, this will look completely standard if you're familiar with secure multi-party computation. If you are not, I'm hoping you just get the intuition that somehow I'm saying that no more information is contained in the obfuscation than in the ideal functionality. Yeah?
Should there be an A in the second, within the second probability, or?
In the second probability.
A of these things.
Yes, that's true. The simulator, you're right. Simulator will, as always, it'll run adversary as a black box and use its output. Yes, you're right. It's sort of implicit here, but simulator depends on A. It's not universal simulator, of course. And the third requirement is, it's sort of natural, it's polynomial expansion. I don't want the obfuscated database, I want it to be within a polynomial factor of the real database, because otherwise, you know, if I could explode it exponentially, you know, yes, I can obfuscate it, but it's not very interesting. Okay, so let me discuss the definition before I go into the construction. So first of all, this notion of indistinguishability from ideal functionality is not always the same as your intuitive notion of privacy. It's kind of orthogonal to it, okay? Because some forms of access are permitted by the ideal functionality. And the goal is not to hide individual data entries, but to control how they can be accessed. Again, using my simple example, obfuscated phone book indistinguishable from the lookup function, it's saying that it's hard to find the phone that you don't know the name. What it does not say is that it's hard to find the name for which there is a phone in the database. I hope you appreciate this distinction, okay? This, you know, maybe you can guess and extract information, a lot of information from the obfuscated database. That's fine, because you can extract exactly the same information from the ideal functionality. I control how you can extract this information. I control the pattern of access. I don't really control the information that you can extract. So this is, I hope this illustrates the difference between giving you no access and permitting some forms of access. And you know, I'm not going to argue that this is the right definition or the wrong definition. That just depends on the application, okay? For some applications, this is right. For some, it's not. So it's, you know, depends on what you really want to do. So let me give you a simple construction. Just for the simple case, it's going to be a very simple construction for this lookup function. So here is a row of the original database, xi, yi, and I'm going to replace it by an obfuscated row that looks like this. It's a random number, then hash of x and the random number, another random number, and another hash of x, XORed with yi. So this is the obfuscation, and I'm claiming this obfuscation satisfies my definition for the lookup function. So why? Well, let me give you an intuitive argument. I'm going to skip the proof. The proof is fairly easy, at least in the random oracle model. It's not so easy without the random oracle model, but for now, let's say I'm happy with random oracle model. And the intuition here is this. If you know x, it's very easy to extract y. If you know x, you can just recompute this hash easily and learn y by XORing. But if you don't know x, or in particular, if you want to learn x from this database, you would need to invert the hash function, which is presumably hard. Okay? So, and the reason you need, by the way, these random numbers is just, you know, for sort of basic reasons, chosen plain text security. It's because if you don't have R1 and R2, then every time x appears in the database, it'll look exactly the same. So that's not a good thing. Okay, so this is a simple construction, and this happens to be an obfuscation. And the reason it works is because this is an obfuscation of a point function, actually. It's an obfuscation on an equality of x. Okay? So nothing particularly adventurous happening here, but it's still a fairly cute construction which allows you to obfuscate exactly what you want to obfuscate. That is, the only way to access this database is to supply x, and then you learn y. If you don't know x, there is no way to learn y from it, and no way to learn x either. The only difficulty here, now access time becomes linear in the size of the database and the number of rows, because you don't know in which row of the database x is. So you have to try your x on every row, see if the second hash if the first hash computed correctly, and if it computed correctly, compute the second hash and extract y. Okay, any questions about this construction? So this is, I hope you see what's going on. You know, I'm just saying that if you know X, it's easy to learn Y. If you don't know X, you cannot learn Y, and you cannot learn X either. That's all, okay? And I hope you see from this thing that if you know X, all the hashes can be easily computed, Y is extracted in no time. And yeah.
You said that access time is now linear in D.
Yeah.
But that depends on your select condition also. If you have 10 fields and you want Y for where one field is equal to something.
Yes.
Is still
it's still linear indeed. If your select condition is only on equality on one field, you have to look at every row and see if that field is in that column of that row. Okay, now let me do something more difficult. Now let me talk to the notion, I'll call it mass privacy or group privacy. Now I want something more adventurous than the lookup function. I want to make it so that extracting one record is easy, or small number of records, you know, and I'll call this legitimate account access, things like responding to a customer request or something. But harvesting many records is hard, okay? So this is like, you know, I give you an email database, and if you really want to send an email to your long-lost classmate, you can do that. That's easy to do if you know his name and the school he went to. But if you want to use this database to send a Viagra pitch to everybody, that is hard to do, okay? So now this is something more complicated than just plain lookup, because I want to draw this distinction between small number of records and large number of records. So what are applications of something like that? Electronic directories, where you prevent malicious users from harvesting information. Things like, I don't know, outsourced customer support. So you outsource it to some place far away, and then in response to a customer request, support clerk can easily look up a number, but they cannot just go into the database and just download the whole thing and send spams to everybody. Things like, you know, multi-institution drug trials where partner institutions don't trust each other. You can share test subject records where you don't know the revelation condition. It's not known in advance. Maybe later on you get some group of symptoms and you want to be open records of all subjects with a certain group of symptoms. But still, to prevent dictionary attacks, you want queries based on partial information should take a long time to evaluate. So this is the intuition. Like somehow if you get one thing, it's quick. If you get many things, it's slow. Let me make it just a little bit more precise. What I want is, I'll call it exponential slowdown. And I'll claim that one thing that separates legitimate questions from mass harvesting is this, that legitimate users know what they're looking for and can describe it more or less precisely. Okay? So give me the email of some person and you can describe this person. But abusers, they just want everything. They want to send email to everybody. They want everybody's information. And so what I'm going to do an obfuscated construction where the idea is this, that if you ask some query of the database, and there are n rows in the database that satisfy this question, then you force the user to guess n bits to compute the answer, okay? So the answer is encrypted and the user learns all but n bits of the key. And you can see what's going on. So if you can describe a record, some condition which is satisfied by 2 records in the database, you'll need to guess 2 bits. That's very easy to do. If you ask some question give some predicate which is satisfied by 1,000 records in the database, you gotta guess 1,000 bits. And that's computationally infeasible. So now the difficulty of access is gonna become proportional, exponential in the size of the answer. And of course, the immediate question is, what can be obfuscated in this way? And I'm going to answer this question in about 5 minutes. So here is, let me give you the formal definition, and it's very similar to what you've seen before. There is a database. Now I have multiple columns, not just one. There is some predicate, and I'll make it more precise what classes of predicate I can support here. And let's say here is a set of rows satisfying this predicate. And now I'm giving you a different ideal functionality, and I highlighted the relevant part. So this is the ideal functionality with exponential slowdown. So if you give it a predicate and the predicate is satisfied by nothing in the database, it just barfs, it returns nothing. But if the predicate is satisfied, then it returns the right answer with probability that's inversely exponential in the size of the answer. Or else it doesn't give you anything. So this ideal functionality satisfies this notion of exponential slowdown. That is, your chance of getting correct information out of that database is inversely exponential in the size of the answer. And I also wanted to satisfy these properties: probably correct retrieval, virtual black box, which is just security, and polynomial expansion. Okay, so even if you don't follow the details of the definition, I hope you understand this part. Okay, that the ideal functionality gives me this property that I want by design. Now the real question is, can I obfuscate so as to satisfy this property, to guarantee that in the obfuscated database this property holds with overwhelming probability? Let me work through a simple example. So suppose I have a list of people, name, year of birth, and email is the field, is the column that I want to protect. Now, if I run a query like this, select email where name is Smith. Okay, there are 2 records in this database, so I want to make sure that user cannot learn email of either of those Smiths without guessing 2 bits. Okay, and if he supplies year of birth, because he only knows year of birth, there are 2 bits that need to be guessed because there are 2 records that satisfy this. But if he gives me this query, if he happens to know both name and year of birth, there is only 1 record that satisfies it. So I want to force the user to only guess 1 bit. Okay, and you'd think, like, why does he have to guess anything? Because this is precisely described, but this is just a technical property that I want. N records satisfy some predicate. I want the user in the obfuscated database to guess N bits before he can get to it. And that'll separate legitimate people for whom N is small and there is a small number of bits to guess from illegitimate users who want to extract everything, and then there are a lot of bits for them to guess. Okay, so here is what the obfuscation look like. And it's becoming a little bit complicated, although it's based on the same idea. Now, again, I try to highlight the relevant parts for you. So let's look at the first record here. You encrypt every field using a hash of a random 4-bit key. And the reason it's 4-bit, it's because, that's the size of the database, 4. And then if you learn if you know the value of a particular field in the column, you don't learn all bits of the key. You learn only some bits of the key, okay? And hidden bits depend on other database entries. Like, for example, if you know last name Smith, in the first row, you learn only 2 bits of the key. And the reason you learn only 2 bits and 2 bits are unknown is because there is another row in the database where Smith appears. So that's why you only 2 bits are hidden from you. You have to guess them. Okay. But if you, for example, know in the second row, if you know year of birth, like 1952, then you learn everything but 1 bit, because there are no other rows in the database where that year of birth appears. So there is only 1 row with this year of birth, so you learn all bits but 1. Okay, and then, as always, to make retrieval possible, you need to help user verify that he found the right row. So every value has to be additionally hashed for verification purposes, because otherwise it's not clear how to do retrieval. So this is just a simple example of how this is done for this mass privacy. And to answer the question, what can you obfuscate? Actually, quite a bit. Okay, you can obfuscate, it turns out, any logical circuit, so and, or, and not, of equalities and inequalities over individual field values. So you can obfuscate any circuit of the flavor if, give me everything where x is equal to something and y is equal to something, or z is not equal to something. That's all efficiently obfuscatable. Okay, so it's not everything you might want to obfuscate, but it's a useful class. Okay, it's more than point functions for sure, and it comes with a proof that the obfuscation is secure. Let me just give you a slightly more general presentation of the same idea. That here is the idea. So you have some fields which are kind of access fields, and then you have data field, and you want to be able to access data field only by supplying corresponding key fields. So if there are n rows in the database, then you encrypt your data with a fresh random key, and the size of the key is n bits, okay, which is equal to the number of rows in the database. And then for each field, for each access field, you make it so that if there are m rows in which the value of x is different, then you learn m bits of the key. Why different? Because if you want x to be, if x is unique, then you should learn this key right away, because this means that the query should not be obfuscated because you uniquely identified the row. But if you supply some common value like zip code or gender or something, you only learn a small number of bits here. And the same thing for y. And of course, the bits you learn by supplying x and by supplying y are different. So that's why it's kind of secret sharing. But here, shares of the secret, they overlap. And the overlap here is the number of common bits is exactly equal to the number of rows where x and y are the same as in this row. Okay, so it's kind of weird secret sharing where secrets are overlapping and the size of overlap tells you something about the database. Okay, so this is as formal as I'm going to get. I actually have the proofs, but I didn't want to dump them on you. So, but I'm claiming that a construction like this is actually indistinguishable from the ideal functionality, or rather can be simulated in the ideal functionality and therefore does not leak any more information than the ideal functionality, where you get the answer with probability that's inversely exponential in the size of the answer. Yeah?
So suppose one key field is name, the other is year of birth. Now, if I try all the value for year of birth, do I get all the keys?
Yes, you would. You would. And because the ideal functionality permits that. Yeah.
But in that sense, it's kind of by issuing multiple queries, independent queries, I can get a lot of information.
That's true. That's true. And that's just all I'm claiming is that I'm going to be indistinguishable from my.
I'm just saying maybe it's more desirable to have some ideal functionality to somehow deal with that as well.
Well, it's hard to find a natural definition because the idea is that if it's a really large database, then there will be a lot of repetitions of common fields. So, like, for example, if half of them have the same year of birth, supplying that year of birth is not really going to gain you anything, okay?
Right.
I mean, if you really know the unique year of birth that's there, yeah, you'll pull it out. But if there are a lot of, think if it's like a census database, there are like, 100,000 people there with every year of birth. So supplying year of birth will not get you anything.
So I'm thinking by issuing 1 year of birth, I don't try to decrypt. I only extract the key bit, and then I issue a query for all other year of birth. Can I get all the key bits before I'm guessing?
So if you just supply 1 year of birth, well, you'll extract key bit. Well, I mean, for the rows where that year of birth is such, yes, because this is done for each row. So but these key bits will be of different keys. Okay. So that's not going to get you all that much. Yeah. Okay. So this is done on per row basis. So these will be key bits of different keys. So, okay. All right. So there are some technical difficulties there. In particular, the ideal functionality is defined as not simulatable, actually. And not simulatable for a stupid technical reason, which, again, if you work in secure multi-party computation, it's kind of the same reason why commitments are not simulatable. Basically, obfuscated database in this construction, it reveals whether the same value appears in multiple rows, because you can just go through the database and test X on every row. But ideal functionality doesn't. And because of that, the simulator doesn't know which equalities to put into the fake obfuscation. So there is a kind of a somewhat unpleasant fix to this, which is, you redefine ideal functionality so it gives out this information. Given a row index and a candidate value for any field, the ideal functionality answers whether the guess is correct. It doesn't really change anything. It's a technical difficulty. I don't know how to simulate if you don't have this information available to the simulator. And it's kind of the basic commitment problem. You have to give the obfuscated database to the adversary before you know what equalities should be there. And normally it would be solved by some kind of rewinding of the adversary. But here, the rewinding argument doesn't work. Anyway, like I said, this is work in progress, so we're hoping to fix that. It's not terrible. And then there are some practical difficulties. Obfuscation of a single row depends on the entire database, and you can see this because which key bits you learn depends on what else is in the database. so it cannot be incremental, and this seems to be inevitable because this exponential slowdown property makes your access time to a single row of the database dependent on what else in the database. So that's just a feature. And then you need this many bits to obfuscate every access. So squared number of rows times the number of columns. This is not great, right? So like you're like squaring the size of the database. It's actually perfectly fine as far as theoretical definition is concerned, because the theoretical definition says expansion has to be polynomial in the size of the database. Well, that's polynomial in the size of the database, okay? But still, to obfuscate a database with n rows, you need n squared extra bits. So, you know, maybe not quite practical yet. But as I said, it satisfies this virtual black box property. And well, let me summarize. So what I hope you've, what have I talked about? So first of all, I'm hoping to convince you that obfuscation is an interesting notion of privacy, that it's somewhat orthogonal to commonly used definitions. So this idea that I make my database indistinguishable from some access function is not quite the same as saying that you cannot get any access to my records. You can ask the question, what are the interesting ideal functionalities? So far we have constructions for lookup and for exponential slowdown. But you know, there are many access patterns that you might want to obfuscate. And it's not clear. I mean, maybe you can, maybe you can't. We thought that some of them could be unobfuscatable, but every time we tried to get an impossibility result, we couldn't, which seems to, well, I mean, maybe we're just not seeing something deep in the problem. But the fact that we have been unable to get a single impossibility result seems to suggest that there are a lot of things that can be obfuscated in this fashion. So the good news is that for a large class of access patterns, we have provably secure constructions. The proofs are in the random oracle model, but you know, for some cases, maybe they can be converted into the plain model. But I guess good for the time being. You know, and practical implementation is still a challenge. We just started working on this. We just got the theoretical constructions right. So at some point, we hope to be able to have some practical tools that allow you to do database obfuscation on your own data, you know. But we haven't gotten there yet. Okay, and this is it. Any questions? All right.
Can you go back to that lookup where you explain how you...
I should be able to. This one. Yeah, sure.
These R1s and R2, are they per row or?
This is for each row.
So they are actually R1I or?
Yes, I'm sorry. These are R1I. Otherwise, you would be able, yeah, otherwise it wouldn't work. Because otherwise, if this value were the same, then you would be able to compute XOR of Y's where X's are the same without knowing X. Okay?
Right, but that is what you want.
No, that's not what well,
like if you need to know Xi to...
But the problem is that if this random number is no different in every row, but X is, without knowing X, you could cancel them out and compute the XOR of two Y's without knowing corresponding X.
And what about indexing? If you like in these kind of databases, can you use indexes and?
I have not thought about it. I'll give you an honest answer. I don't know what to tell you. Yes.
So in the second version of this, where you had the choosing n missing bits, how do you do insertions? Because it seems that if you want to insert a new row, you have to recalculate the.
Oh yes.
And you don't have the original index value. You don't have the xi value, right? So you have to guess what xi is.
Yeah, you cannot really do insertion because your access time has to depend on what else in the database. So if you insert and you think you're potentially changing access time for every other row in the database. So like I said, it's not real incremental. It's designed for situations where you take your own database, you obfuscate it, and you just give it to other people, to everybody, and have some notion of privacy. You cannot later add data to that database, at least in the current construction. Yeah.
When you submit a query and the query returns some records with n missing bits, so the next step is you have to guess.
Okay, it doesn't return records with n missing bits. It returns the key to those records with n missing bits, okay? And and since this key is used as an input to a hash function, the idea is that you need to guess those bits before you get to the record. So I'm just being very precise here. You get all but n bits of the key. You don't get anything of the record until you get the key. Sorry, I didn't mean to interrupt.
Okay.
So there is no partial leakage of information until you got all bits of the key. Did I answer the question? Oh, okay, sorry. Yeah.
So as a legitimate user, I don't know which guess is correct.
So this is what this field is for, so that you can verify your guess of X. That's exactly what it's for. And I don't know how to obfuscate without it, and that's why I had to hack ideal functionality, so it tells you when your guess is right. Okay.
How is that achieved in the second approach?
In exactly the same way. Like, see, this helps user verify that he found the right row. So for every value that is there is a verification. And we're hoping to get a construction where you don't need that. But it's hard. It's hard to get simulation working if you don't have that, because the simulator needs this to simulate. I mean, it's just hard to figure out. Like, no, I'm sorry. What I meant to say is that if you want to do retrieval on this like sort of multi-column database, you need to know that you're in the right row. At some point, you need verification that you're doing it right, because you need to know which bits to guess, okay? So somehow there has to be some indication that tells you which bits you need to be guessing, or at least how many bits you need to be guessing.
How does one know whether he gets correctly, incorrectly, even the key bit, if you need to get two bits?
Yeah, assume that there is some redundancy in this field. Yeah, so he recognizes that. Right. He puts it through the hash function, then he has to decrypt and see, you know. And you can see how this is done in the random oracle model. It's kind of easy. Any more questions?
Sorry. Is this method only applicable to the keys? How about the non-key fields, if they're different keys? And
I'm not sure I understand the question. What do you mean it's only applicable to keys?
I mean, the keys, they have to be distinguishable from each other, so that unique primary key field.
No, I mean what I call like here, what I call key fields. No, they don't have to be unique. This is just a database. I mean, these are used like hashes of these values I used to learn the key, but they don't. I mean, I call them keys, but maybe this is misleading. These are not cryptographic keys. This is the actual data in your database, like names and so on. So they don't have to be unique now.
I think what he's saying is this notion of key versus database notion.
They're not database key.
Oh, they're not database keys. Yes, I'm sorry. I'm okay. I apologize. This is like terminological confusion. This is not a database notion of a key. No, this is just some fields.
Any other questions? Thanks, the speaker.